The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. Welcome to the Sustainability webinar. I am Beth Mashesky, Senior Scientific Specialist at the Illinois Sustainable Technology Center, which is part of the Prairie Research Institute at the University of Illinois. A few housekeeping items before we get started. You can download the slides to this presentation in the handout section of the GoToWebinar toolbar. The recording and slides will be available online about a week after the presentation concludes. I will be sending an email to everyone who registered for the webinar when the recording and slides are available. Everyone will remain muted for the entire webinar. We will be taking questions at the end of the webinar. You can type in your questions at any time through the GoToWebinar toolbar, and I'll be reading those to the speaker at the end. And so with that, I'm very pleased to welcome today's speaker, Ned Beecher. Ned is a Special Projects Manager with the Northeast Biosolids and Residual Association, which is abbreviated to NEBRA, and serves to advance the best practices and sustainability of biosolids recycling. Ned earned his bachelor's degree in geology from Amherst College and his master's in resource management from Antioch University. He previously served as the executive director of NEBRA for 11 years, where he tracked research, legislation, regulations, and provided information on biosolids to NEBRA members and the public. In his current position as Special Projects Manager, his research primarily focuses on the role of PFAS in biosolids. So Ned, thank you for joining us, and the webinar is yours.
Thank you very much, Beth. I assume you can hear me okay?
Yes, we can hear you.
And thank you all for joining this webinar. I hope everybody's doing okay in these times, unusual times we're having now. And webinars are one way we can continue to learn and share information and be together as a community. So thanks for participating. I'm going to run through a whole variety of slides. I have quite a few. And as Beth said, the slides are available through download from the GoToWebinar site and will be available later, as well as this recording. So I will skip through some slides fairly quickly, and you can go back and read them as needed. So NEBRA is a group that advances biosolids recycling in New England and Eastern Canada, providing a variety of services to members and the general public and other stakeholders. I'm going to stress at the beginning of this presentation a little background on what biosolids recycling is and why it is being done and what is involved in it, because that's important context for understanding contaminants of emerging concern that appear in biosolids and wastewater, and in including PFAS, a current contaminant of emerging concern that is getting a lot of attention these days. So wastewater and biosolids and other organic residuals are recycled for a reason. Sorry. They provide farmers and communities benefits, which are shown here: enhancing soil health, recycling nutrients that come from our food and our feed crops that are recycled then back to the soil. It's an important piece in sequestering carbon, along with other organic amendments like animal manures. Returning that carbon to the soil is important. Biosolids recycling can help reduce local fertilizer and pesticide use, strengthening farm economies and neutrality to degraded lands. And probably the most important aspect is that there's some material that needs to be managed. Wastewater treatment is an option. It's critical for public health, and it produces biosolids or wastewater solids that need to be managed in some way. So biosolids recycling is seen as an important part of the circular economy. And the key point of it is to try to maximize the beneficial uses of these resources in biosolids, the water, the organic matter, nutrients, and energy, while minimizing potential risks, which includes trace chemicals of emerging concern. In the U.S., about 50 to 60% of biosolids produced at our wastewater treatment facilities are recycled to land in some format. And it's done because it's important for soil health. This is a summary of some of the benefits from the University of Washington's research, and there's plenty of documented published papers that support these concepts. When you add organic matter to soil in the form of animal manures or biosolids, you increase the carbon in the soil, which is important for healthy soils. You increase the microbial activity considerably. The water holding capacity can be increased dramatically, which can reduce the need for irrigation, and bulk density is reduced, which makes the soil more manageable and handleable. And there's been research to look at the various ways that biosolids and, frankly, other organic materials such as food waste and animal manures can be managed. And if they're put in a landfill, that tends to create a great deal of methane, so the greenhouse gas emissions are considerable. If you incinerate them, it depends somewhat on some of the factors of incineration. You can have fairly moderate or low emissions from incineration if you do it at high enough temperature. But when you land apply and use anaerobic digestion, for example, you can end up having much lower emissions. Biosolids are used in many ways then, and I'll run through a few quick slides on how they are used. One is for energy. Anaerobic digestion is becoming a very large portion of what's being done with biosolids prior to their being land applied. Anaerobic digestion and co-digestion with food waste and other organic residuals can provide a source of natural green methane, which is then used for green electricity and heat, and can be used even as a vehicle fuel when refined. So it's a useful way that every municipality can generate some renewable energy. Biosolids are used widely in agriculture. As shown in the middle here, the biosolids tend to do a good job in increasing plant growth and vigor. And so this is the most common use of biosolids nationwide. Forest productivity can be increased, and this is common in the Northwest and a few other areas of North America, where a one-time application of biosolids can result in a significant increase in the growth rate of trees that are heavily managed for productive forestry. Composting of biosolids has been going on for many decades, and it is the material is used in a variety of horticultural and landscaping purposes and has been for decades, as shown here. A couple of sites here where biosolids compost was used in the past, the Liberty Park in New Jersey and the White House lawns back in the 80s. So this has been going on for quite some time. Perhaps the most exciting and greatest use of biosolids is for land reclamation. This is where you can take a despoiled piece of land or a mined area and create a natural ecosystem without having to import soil from farm fields or other sources. Biosolids mixed with other organic residuals and sand can create an engineered topsoil that provides a long-term solution to some of these despoiled sites. This is an example from Leadville, Colorado, a Superfund site that was restored. And this is from Western Pennsylvania coal mine. Again, the restoration that can happen with a single application of biosolids and other materials mixed in an engineered soil is significant. Finally, one more site. This is going back to the 1980s. This dead ecosystem on Blue Mountain was then revegetated with biosolids. And the interesting thing here is that one area of along the Appalachian Trail at the top of the ridge was not vegetated, so it serves as a control to indicate the difference between what you can do with biosolids and what happens if you don't revegetate an area. There are many other uses of biosolids as well. Landfill closure and methane mitigation. By having a robust soil, you can reduce the methane rising from a landfill. You can treat landfill leachate through a robust soil ecosystem. You can sequester greater carbon by adding organic residuals, biosolids, and others to a soil to increase plant growth and sequestration in the soil as well. And acid mine drainage can be reduced with a treatment system with an engineered soil rich in biosolids and other organic materials which treat the drainage. So anyway, I give a recommendation to this particular film. If you aren't familiar with biosolids recycling, it's an overall view of it. I'll look now at all the research that's been done on this. And the reason we raised the research question is that contaminants of emerging concern in biosolids and wastewater have been studied for a long time. Different contaminants at different times, different chemicals, different and heavy metals in the past. So the research and how to go about it is well understood. The risk assessments are continuing to develop, but have been used for a long time. So there's a lot of work to build on, and as we look at the current contaminants of emerging concern. I love this classic photo from the 1970s of the biosolid, the corn on the left being basic control fertilizer plot, and the corn on the right, more robust, showing that there are significant measured benefits of using biosolids. Another classic photo from research in the 1970s at a coal mine that's been revegetated with biosolids. And when we look at what has been done at these sites, there's not just use of the biosolids, but considerable research. So again, Penn State University, William Soper work from the 1970s and 80s, and Chicago area, the Fulton County land application sites have been researched heavily, and there are many published papers looking at long-term uses and impacts. Same with the Rosemont, Minnesota sites, where University of Minnesota and others researched for a couple decades. And Denver's Metro Grow Farm, where biosolids are used in classic ranchland agriculture, again, has been studied and measured and restudied and measured further, as have the King County biosolid sites in eastern Washington, where biosolids have been used, again, for decades. Loop is the name of the biosolids that are being produced in Seattle, the King County area, and Loop is a brand name for that biosolids material. And this graphic from the Loop program sort of demonstrates the benefits of, summarizes the benefits of using biosolids. Sometimes it's a lower cost option in many cases, but it also provides the benefits of recycling your nutrients, as mentioned earlier, and it can be part of a climate change solution in comparison to the other two options for what we do with wastewater solids, incineration or landfill disposal. And if you look around at different land-grant universities and their extension programs, most of them have biosolids utilization advice and guidance documents going back, again, decades. And then to summarize the research, every 10 years there's been a State of the Science conference organized by EPA and USDA and other researchers, dating back again to the 1970s, starting out in Illinois in 1973. And coming to the present day, plus there's ongoing work of the U.S. Department of Agriculture's W4170 Residuals and Soils nationwide research group on the use of biosolids and other organic residuals. And there have been 2 National Academy of Sciences research reviews of the biosolids regulations at the federal level. So research is continuing, and especially CECs continue to get attention. As I mentioned earlier, risk assessment is a key aspect of this. So there are trace chemicals in many different materials, manures, fertilizers, and biosolids, things that are applied to farms, things that are used on land. Trace contaminants are there. So risk assessment, understanding what the potential fate and transport and impacts of those trace contaminants is a critical aspect of the science on this. So the presence of a contaminant in biosolids does not mean there is risk. Its fate and impact on humans and the environment must be evaluated. So when we look at, this is the EPA model that's been developed over decades really and is continually being developed and additional pathways being added as needed. But this is the basic model of how use of biosolids on a farmland might impact humans and environmental biota and systems. So the pathways as originally laid out are 14 of them in all. Additional ones are being considered, but they basically have pretty conservative assumptions and assume a 70-year lifetime, etc. And these are the pathways that have been looked at for biosolids contaminants and continue to be used in that way. Having summarized the research then, going back a long time, we also can look at the fact that biosolids have been used widely in many different climates and places around North America as well as around the world. So it's an ongoing practice, not something new and different, but it's been an important part of managing wastewater for many, many years. But here we get to the main topic. What about the contaminants of emerging concern? So contaminants of emerging concern, according to EPA and others, are trace chemicals and other materials, elements that the interest in is growing because of our ability to analyze them in smaller and smaller quantities, perhaps. But these contaminants may have been around or may be around, and what is really emerging is the interest and the concern regarding them. So there are many different ones in biosolids. Biosolids are a reflection of modern life. PFAS is what we will get to at the end of this presentation, but is certainly a current concern for waters, wastewater, and biosolids today. But it's not the first. We've had trace chemicals being researched in biosolids for many years. There was research that sort of got the CEC thing going in the late 90s, showing that USGS conducted, showing trace contaminant chemicals in various streams all across the United States. In 2003, EPA conducted a robust review of dioxins and furans in biosolids. And we have considerable information on our website. More recently, personal care products or pharmaceuticals and personal care products, PPCPs, have gotten a lot of attention in various published papers, looking at medicines which obviously get in biosolids either through us or in our waste products or through introduction of people inappropriately disposing in the toilet or something like that, some of their unused medicines. So hygiene products and personal care products often obviously end up in wastewater as well. Microbeads used to be an issue, and now we have PFAS. But some of these things, the best way really to get rid of them of the concern in biosolids and wastewater is to get them out of commerce if they are serious public health or ecological concerns. And that's happened with a number of these, including microbeads. So research on CECs, contaminants of emerging concern in wastewater and biosolids, really blossomed in the 2000s and to the present day. There are a number of papers that are listed here that looked at what happens with the presence, essentially, of these in biosolids. And some of these are kind of seminal papers, like some of the work by Kinney and Furlong at USGS, Halden's work And also, I list these. I won't go into all the details, but the reality is that they show that yes, wastewater and biosolids have traces of pharmaceuticals, personal care product chemicals, and etc. In measurable amounts, usually in low parts per billion, and that these chemicals can be researched by looking at what are the major production chemicals, which ones are being used and produced the most and end up in products the most, and thus we look for those higher priority ones, higher use ones when we look at wastewater research and biosolids research. Ellen Harrison and others at Cornell put together a paper looking at the literature back in 2006 and identified the levels in biosolids and other residuals. And Kinney, the USGS work, again, seeing that there is there are levels in biosolids of various trace chemical contaminants such as triclosan, which is an antibacterial found in soaps, now has been phased out, but it used to be one of the most common antimicrobial ingredients in hand soaps. And in toothpaste and other products as well. And here we're looking at micrograms per kilogram, which are part per billion. These are getting up into the 10 part per million level, that the triclosan in the biosolids. And there was considerable research done on that. Here was a seminal paper by Clark and Smith, 2010, which is showing the levels in wastewater. In biosolids generally, and most importantly, it's showing the here we're seeing the PFAS chemicals showing up down in low concentrations, but still measurable. So fate is the next area of important research. So yes, these things are present. So what happens to them when they are in biosolids? What happens in the wastewater system has been studied quite a bit. Many of the trace chemicals that we use in our daily lives are broken down by the physical and biological processes in a wastewater treatment facility. Some, depending on their structure and chemistry, will go into the air perhaps, or stay with the water in a wastewater treatment facility, and some will end up in the biosolids. And when they're in the biosolids, what does that mean? That's the subject of research, and these are some of the seminal papers that have happened over the years looking at field applications of biosolids and what happens with some of the PCPs and other trace contaminants of emerging concern in the biosolids and in the soil ecosystem. Work in Ontario by Ed Top and his group looked at PCPs, various pharmaceuticals and personal care product chemicals, some of these, and the maximum concentrations of the various PCPs detected in effluents, that is in the shallow groundwater and tile drainage, were generally far below toxic thresholds for a variety of endpoints drawn from the literature. Work in the Chicago area by the soil scientists at Chicago's wastewater treatment facilities and associated colleagues found, for example, that with triclosan and trichlocarbon and other contaminants, including polybrominated diphenyl ethers, flame retardants, PBDEs, the presence of those in biosolids and their persistence in the biosolids means that they do show up in the soil. They're greater in the biosolids-amended plots than in the control plots, but they did not find any detrimental effects on the soil biota. Microbial studies showed that microbial populations were more diverse and more biologically active in the biosolids-amended plots. So, and that's what we have seen in research all along, is that adding nutrients to soils increases the biological activity. So if there is any negative impact from these trace contaminants, they are overwhelmed by the benefits that adding nutrients and organic matter to the soil produce. One interesting study that was done again on personal care products. Triclosan was showing, was the Wu et al. Study in 2010, which got quite a bit of media attention. It is an important example of an important distinction to make about research studies. So this was a proof of concept study where it was done in a laboratory and greenhouse, and the soil samples were spiked with fresh contaminants. This is not uncommon to have this kind of experiment, but it's important to recognize that what past research has shown that overestimation of the effect is generally shown when spike samples of the pollutant are used in these kinds of microcosm studies. They are not representative necessarily of what will happen in the field. One of the things that's important to note also is the context of the Wu study. The idea that human exposure could happen through biosolids, sometimes that sounds like it's might be a little scary. So there's triclosan and biosolids, but what's important to note is how much. They measured some plant uptake, again, in this highly conservative study of 0.1 milligram per kilogram or part per million. And that, raised some concern. So are people eating this material in food? Well, again, this is a spiked study, and the plant uptake in the field has not been shown to be that high. Plus, the toothpaste we were using at the time had 3,000 parts per million in it. So context and numbers are important. And again, what research by Tom Young and others at University of California, Davis showed that increased nitrogen added with biosolids stimulates nitrogen cycling sufficiently to offset any detrimental impacts on the nitrogen cycling caused by this antimicrobial triclosan or triclocarban. Plant uptake, again, has been looked at, but here in this case, it's done on a field level scale with a real biosolids land application scenario where more than 100 or 141 total analytes were looked at, and crop uptake was evaluated in the field in real world conditions. So no analytes were consistently detected above any detection level at 3 triplicate retreated plots, and the study suggests that the potential for micropollutant uptake into crops under normal farming conditions is relatively low. There have been 2 significant studies out of, or reviews of the fate and impacts of biosolids and trace chemicals. One is by Monteith et al. In 2010 study that looked at the fate of various trace contaminants going through wastewater facilities and then biosolids processing. And what's interesting to note is that the biological process is used to manage biosolids to make them more stable and reduce pathogens in them, which is necessary in order to use them by regulation. They must be treated to reduce pathogen load and make them stable so they don't create unnecessary odors and nuisance and vector attraction. These processes, the ones that work the best to reduce trace chemicals of emerging concern, are the biological ones. So that's what that study showed. One of the worst case scenarios that we've had when looking at CECs and biosolids and wastewater have been the dioxins. There was a major review done in the early 2000s, and EPA decided not to regulate dioxins and furans in biosolids because of the findings of that review, that they presented minimal risk at the levels that are found in biosolids. A second major review it came out in 2015. This is a current go-to for understanding risk associated with application of municipal biosolids. It has a great deal of information on CECs, generally showing that if there are impacts, they're minimal and are overwhelmed by the positive impacts of adding biosolids to soils. But there are ongoing CEC concerns being researched, and this is important. Antibiotics continue to be a question that comes up. There are a lot of antibiotics used both in manures, actually more in manures, but also found in biosolids. And when those are added to soils, what is the impact of the antibiotics? Are they creating antibiotic-resistant gene profiles in the soils? Are they having impacts like that? It looks like probably not. Research to date, work by Ian Pepper and all at University of Arizona, summarizing that kind of work is showing that. But other questions include nanoparticles. We have silver nanoparticles in some of our clothing for anti-odorant use. And what happens when those get into the soil? Well, again, some important research has been done on that. Again, it's silver. Silver exists in other ways, and metals of that sort tend to be bound fairly strongly to the soil. Flame retardants, PBDEs, have been looked at. Some are being phased out now because they are persistent organic pollutants. Their fate in biosolids-emitted soils have been looked at, and because they're persistent, they tend to sit there. They don't seem to be taken up by plants and don't migrate, but they are something continue to be researched. Things like synthetic musks in some of our personal care products, those have been looked at. And now microplastics is a growing issue and something that's getting more public attention. Microplastics come from many, many different sources, and biosolids is not a major source on farms, according to a Danish study that was done, came out last year. But that will be something that continues to get some research. I think generally it's important to note that these are important topics. The CECs and biosolids being land applied is something that deserves research attention, but it's the risks associated with these appear to be relatively low, especially compared to, for example, some of the heavy metal issues that were dealt with in the past and have now been controlled through both source control and pretreatment standards and regulatory standards that limit the heavy metals being applied through biosolids. Pathogens also being an issue that needs to be addressed and is perhaps higher priority risk and is being dealt with, again, through regulations and best practices and requirements to ensure that impacts from pathogens from biosolids are not found. So, trying to summarize what the CEC concerns are with biosolids in particular, CECs are in biosolids because they tend to stick to the solids. They absorb strongly. There's kind of a choice in the wastewater facility. Those chemistries that sorb to solids go with the solids in the separation process in wastewater facilities, whereas those that are more soluble stay with the water. When they have stuck to the solids, they tend to stick to the solids continually, even when they go into the soil. And many of them are broken down naturally through microbial biodegradation processes in the soil. But, papers summarizing this have shown that these particular attributes will create greater concern for particular CECs in biosolids. And Kumar and Gupta's paper in 2015 kind of summarized, again, some of these concerns. This helps better define and refine and screen the screening processes to make research on biosolids contaminants as effective as possible. So it's the research continues and it's challenging. So one of the problems, of course, is that there are thousands, tens of thousands of chemicals, synthetic and others, in use in commerce today. So what a costly process it would be to go chemical by chemical. Of course, many of them can be screened fairly quickly and shown to be not a concern, but there are enough that, there's not enough information on or may raise initial concerns that it's hard to go chemical by chemical. Research has done a good job, but it could take a long time to get it. One screening approach that we promote and we encourage is sort of the use of bioassays. It's a logical and efficient approach to assessing potential impacts of an addition to a system, such as biosolids to a soil ecosystem. It addresses concerns of the impacts of mixtures. Biosolids is a complex mixture. addresses concern of persistent exposure. The idea that there might be, chemicals that will be breaking down. The vast majority of chemicals in biosolids, synthetic chemicals, do break down in the soil, but if you have repeated applications, you could have persistent exposure of the short-lived compounds. And so bioassays can help address that, and it improves understanding of the full system. So again, this kind of full system evaluation research has been going on. It goes back to the 1970s and 80s when, again, the SOPR work at Penn State looked at rabbits' health at reclaimed biosolid sites. The same when Sally Brown did her work with USDA at the Leadville site in Colorado, looked at rabbit health as well. Not looking just at the plants, but also animals that are living on the sites that have been reclaimed with biosolids and testing to see if they are impacted. And what we find is that they are impacted in a positive way in that they can live there now. There's vegetation for them to eat, and they thrive. Most recently, there's been some work done in Canada. Linda McCarthy's team looking at earthworms and springtails and plants and even aquatic organisms that receive the runoff from biosolid sites to see what the impacts are. We'll talk more about PFAS in a minute, but remember for now that all of this historic biosolids research included PFAS, whether we knew it or not, because PFAS were in use then too, and were likely in all these biosolids that were applied at these sites in levels perhaps a little higher than the levels even today, at least for PFOA and PFOS, which have been phased out. These are the various organisms that were tested by the Pudafat and McCarthy research, and the findings showed that biosolids had a little negative impact on the terrestrial biota examined. There's no impact observed in general. Where effects were observed, the majority of instances are positive in that, again, you add the nutrients and organic matter, and you have benefits that outweigh any of the trace negatives. But this is the kind of work that has been done. Most recently, I'll mention that in British Columbia, there's been a study of sites where biosolids were used as compared to sites where biosolids were not used in similar landscape ranch areas. And the number of the variety of endangered species of birds and such was found to be higher in the biosolids sites. And that makes sense because they are richer ecosystems because of the added nutrients and trace elements, trace nutrients, as well as the major nutrients. So they are more productive even and beneficial for these endangered species or rare species in that ecosystem. Remember that context is important. So this is a useful document from the Northwest Biosolids, putting it into perspective. How does using biosolids or compost made with biosolids compare to our everyday exposures in life? So this is a fun graphic and just from that document, just showing that it can take a really long time to get the equivalent of one dose of or one use of something that we do in our daily lives if we do it through typical exposure to biosolids. And it's kind of a funny thing to think about, but 216 years on the left side here is what would be needed as your sort of typical tractor driver farmer who's using biosolids exposure to get the equivalent of one hand washing with regards to triclosan. So again, context is important. We are not, as the general populace, we are not much exposed to biosolids. That is not a route of exposure we need to be worried about. Again, if you wanted to get headache solved with a couple of tablets of Tylenol, the amount in biosolids is so small that you'd have to, for equivalent of dose, you'd have to consume 2 trucks of loop biosolids. So let me get into PFAS then, and we'll run through that. This is an extreme worst case CEC and the only common trace contaminant of drinking water that's regulated in low parts per trillion. And that makes it different, as we will see. So PFAS, I'm assuming you have some sense of what it is. These are I'll go back, and these are in the upper left. You see the two most common ones, PFOS and PFOA. These are the sort of non-stick Teflon, Scotch Guard, firefighting foam chemicals that are quite persistent in the environment, very persistent, and they are made up of long chains of carbon and fluorine bonds, which is one of the strongest bonds in chemistry, and they have unique properties of being both repellent to oil and to water. So they have many uses in society. They're widely used, and you can look up more details on them. But I'll jump to the idea that they are in wastewater and biosolids, of course, because wastewater and biosolids mirror our daily life. As I've been saying, chemicals of emerging concern in wastewater and biosolids, many of them are just from our everyday lives. Some are from industries, but many are just in our daily lives. Even small town, purely domestic wastewater has been found to have PFAS in it. I have not seen any data showing no PFAS in wastewater or biosolids. We are aware of them in part because of the advances in analytical chemistry. We can measure at very low levels. There are many different uncertainties still. This is a developing research area. There have been hundreds and maybe thousands of papers at this point on PFAS over the last 10 to 20 years. The increasing number of research papers is dramatic over the last 10 years and continuing, looking at the health implications in particular on human health, but also looking at fate and transport in soil systems and water systems. And the science is still developing. There are definitely health implications, but the extent of those and how significant, yes, this is something to pay attention to and to address in public health and in drinking water and food in particular, but there is debate about how extensive and how far it needs to be. We need to go. There are differences between the different PFAS, and there are some 4,000 or more in that have been measured or in commerce or known. Precursors, that is more complex PFAS chemicals that break down to some of the more persistent long chain PFAS chemicals, adds complexity, so it's quite complex, the fate and transport in the field. Analytical methods are still being developed for anything but drinking water. Although there are plenty of labs providing services, and the testing has gotten better for things like soils and biosolids and groundwater and surface waters, but the analytical methods are still definitely being developed, and the fate and transport in soils, which relates to biosolids application, is continuing. Why is there concern about PFAS in wastewater and biosolids? Well, for biosolids and if wastewater is used for irrigation, it really has to do with the fact that PFAS will leach some in soil, and different PFAS will leach different amounts because each one has somewhat different chemistry. And you add that fact to the fact that some states and jurisdictions are regulating PFAS at pretty close to background levels in some instances, and leaching from biosolids or wastewater applications will not be able to meet those standards if those are groundwater or drinking water standards. So, for example, New Hampshire has MCLs, that's maximum contaminant levels for drinking water, and ambient groundwater quality standards that are in the teens of parts per trillion. Those are actually on hold now by a court order, but those are the regulations that were developed, and some other states have begun to go as low in groundwater and drinking water standards. So this is to address this, there will be considerable costs. And the challenge really is that even septic systems, home septic systems that are the way that a good portion of some states, for example, Vermont, more than 50% of the state residents are on septic systems. Even those septic systems are putting out traces of PFAS from our daily lives, from carpets and cleaning and etc., that are in levels that are close getting close to those New Hampshire groundwater and drinking water MCLs. As this study from Cape Cod shows, again, on the left here are the PFAS chemicals that were tested in this particular study, and they're a little below. They're between 1 and 10, and some are reaching into the teens or higher. And again, that's just from home septic systems where there was no known industrial source. It's important to recognize, too, that, there we're talking about kind of the ambient background levels in septic systems and in wastewater and in most biosolids, but there are two major sources of PFAS in the environment, and the ones that have gotten the vast majority of attention are industrial discharges and firefighting discharges, and we'll go through some data quickly to kind of highlight this. A couple of industrial high-profile sites are the DuPont plant in Parkersburg, West Virginia, and then Cottage Grove, Minnesota, where 3M. These were both manufacturers of particular PFAS chemicals, so they impacted their sites and areas considerably. The other firefighting activities are the other major source of PFAS contamination, and here we have on the right and top. Spraying of firefighting foam, AFFF, often called, for controlling a jet fuel fire at an Air Force base in New Hampshire. These kinds of scenarios have played out at military sites all across the country. And the significant thing to note is that the contaminations that have happened there, if you look at the Environmental Working Group maps of these sites and click on them, many of these industrial and firefighting sites have very high levels found in various wells and drinking water or groundwater in tens of thousands of parts per trillion, as shown here for firefighting sites as well, really high levels. In comparison, you look at the background levels, again, that were most wastewater, most biosolids, and other residuals reflect these more background levels. And this is a slide from Bradley Clark in Australia, again pointing out the idea there is this significant difference between the point sources with large impacts, which is where most of the attention has been, and then this ambient background. So compare these data that I'm showing you regarding waters, various waters. For example, PFAS levels have been found in precipitation. A report from the National Atmospheric Deposition Program not too long ago found up to 5 parts per trillion in rainwater. So it's there's an atmospheric component. Looking at data in groundwater, again, EPA has a public health advisory guidance level of 70 parts per trillion for the combination of PFOA and PFOS. Some states have gone lower, but if we look at a biosolids or a residuals management facility, actually was using paper mill residuals for composting. This is a site that was investigated in 2017, and the 70 part per trillion drinking water advisory of EPA was exceeded, so state regulators were concerned. Again, at monitoring well, nobody's drinking that water, but it was above 70 at 95 parts per trillion and 65 parts per trillion. So PFOA and PFOS was up to 160, which is well above the 70 part per trillion standard upon sample also. So this raised some concern on regulators' parts. And this is a wastewater treatment facility shown here with part per trillion PFOA and PFAS levels summed together, and showing, again, compare this to the 70 part per trillion EPA standard and guidance value, and you see that some of the levels are higher in monitoring wells. Again, nobody drinking the water here, and no drinking water wells nearby were impacted. But it is something that raised concern around wastewater and biosolids being a potential source of PFAS in the environment. Looking at wastewater itself, we can see this graph from New Hampshire Department of Environmental Services showing that every wastewater tested, the influent, INF stands for influent, EFF is for effluent, so the incoming wastewater and the outgoing wastewater at wastewater facilities all show PFAS of various sorts that sum together, tend to some of them are above the 70 part per trillion when you sum PFOA and PFOS together. So these are ubiquitous, and we are regulating them or evaluating them at very low levels when we're going into low parts per trillion. Landfill leachate also ends up having naturally having PFAS in them. Again, the leachate is from percolating water through a landfill where the various waste products of our society are disposed, and you end up having parts per trillion, up to thousands of parts per trillion in North American landfill leachates, much higher in some other countries like China, where a lot more manufacturing and waste disposal is done of these compounds. So this is a concern when it comes to how this impacts wastewater treatment plants. This was an article from the Boston Globe last November. And when you did the math and looked at the actual impact, the mass of PFAS that was applied or brought into that wastewater facility compared to the mass that's brought in just on everyday household wastewater, because the landfill leachate is a relatively minor portion of the flow of the wastewater facility, it may have contributed at the most 2% of the total PFAS mass going into that wastewater facility. So again, it's important to recognize that, and the state of Vermont and Australia have looked at this landfill leachate input issue and don't consider it to be a significant source for most wastewater facilities. And then there's data on what's present in biosolids, and again, compare this to what we have for screening values so far. New York has a screening value used in one instance for one permit, really for 72 parts per billion. Maine used numbers that we think are inappropriate because they're based on modeling from underground storage tanks in the single parts per billion for biosolids. And most biosolids exceed that. So here's a well-known data set from Purdue University showing at the top that leaves and grass and backyard compost without food waste in it has some measurable biosolids, but very minimal. But when you get into food waste and compostable food serviceware compost, you'll find PFAS up to 50 parts per billion combined, and biosolids composts will have higher, and biosolids fertilizers will have higher levels, as shown at the bottom of the graph. And when Maine did its testing of biosolids, some 50-some samples were showing a mean of 8.5 for PFOA and PFAS at 25.4. And there's some context here to show some various levels of PFAS in biosolids, which I'll let you look at later. When we look at just background soils, and the state of Vermont did an extensive study looking at this. Again, they found this is nanograms per kilogram on the upper right. There were 8 locations more than 5,000 nanograms per kilogram, which is parts per trillion. So when you put it into parts per billion for comparison, their background levels were up to 5 or higher parts per billion, which when you look at that main data, you're kind of in the same ballpark. So even background levels where no big known sources or existing, has PFOA and PFOS and other PFAS chemicals. Biosolids amended soils, the main data shows these levels. So those are kind of the background things, but there are, of course, wastewater facilities and biosolids where there are direct discharges, large discharges from manufacturing facilities. And in those instances, the biosolids can be of concern. And that is what is true in these 3 instances noted here. Although the main farm situation does not seem to be related to municipal biosolids, there's some other industrial source of the PFOS that's causing the problem there. But again, the solution here is to keep industrial discharged PFAS out of wastewater, and that's what the profession is working on now. We've looked at some modeling that would suggest that the 70 parts per or 72 parts per trillion per billion. This should say, parts per billion is that New York has a screening value of 72. That seems to be more in the order of what would be appropriate for biosolids and soils. So the current regulation of PFAS has created some significant impacts on biosolids recycling. Again, biosolids recycling to soil is a common practice nationwide. Many communities have invested millions and millions of dollars to have that be their outlet for wastewater solids, which have to be managed. And right now, data does not suggest impacts on food products from these, and no significant impacts on waters from biosolids recycling ongoing for a long time. But the uncertainty around the PFAS issue is forcing biosolids to landfills at higher costs. Some situations here in New England, we have some biosolids going out of state at very high cost. And this is raising liability concerns for wastewater facilities, water resource recovery facilities, and disrupting the biosolids management marketplaces. So we can look at a few examples. One is in a couple of communities in New Hampshire have had their biosolids management costs double. Farmers have had to increase their costs by using fertilizer instead of the biosolids they had relied on for years, etc. And the thing is, if you go lower and lower with your regulations, you end up causing additional costs. Michigan has had to stop a few land application situations, and those communities are bearing greater costs. So the advice for PFAS or wastewater and biosolids management is, do you want to test if you don't have to? It is a good thing to at some point, but be careful to develop a sampling plan that's well thought through and how you're going to manage the data and communicate about them. Look upstream for industries that may use PFAS. That's going to be the easiest and most cost-effective way to reduce levels, especially if there's industrial inputs. It's going to be harder to get the PFAS out of the traditional basic wastewater stream because it's coming from all of us in all our homes and small businesses. Track what's going on with this issue in your state regarding PFAS. So in summary, how do we want to manage CECs, contaminants of emerging concern in biosolids and wastewaters? There have been significant impacts to biota measured in aquatic environments. That's where the concept of the sort of feminization of fish and frogs downstream of wastewater facilities has been measured, significant issue, but these kinds of impacts have not been seen in biosolids amended soil. So really getting these trace contaminants into the biosolids so that they can be managed either through recycling or incineration or landfill disposal is the right thing to do. And that's what wastewater facilities try to do. They try to separate out any contaminants that could impact the aquatic environment. Risk to human health through biosolids application to soil pathways appear to be negligible still, even after all the studies, but ongoing research is important. Far greater exposure to many of these CEC chemicals is through our daily use of products. Source reduction should focus on the most persistent compounds with known or potential toxicity. And as I said, if we're wanting to support recycling of biosolids as well as protecting water and environment, then a lot of these trace contaminants we'll be fine with if they go into the biosolids and into the soil, because the large majority do break down in the processes and in the soil. These terrestrial systems have orders of magnitude greater microbial capability and residence time to achieve decomposition and assimilation compared with aquatic systems. And again, focusing on biosolids quality, this is happening. This is happening, for example, here in New Hampshire, where New Hampshire DES has an excellent program on biosolids improvement related specifically to PFAS, where communication upstream to consumers and others is helping to control the amount of PFAS and other trace contaminants coming down the wastewater stream. Wastewater is a recyclable resource. It needs to be managed. All of us can do our part in reducing the inputs to wastewater, not using toilets as disposal facilities, putting only human waste and toilet paper down them, and that way we'll all protect wastewater and the biosolids. So phasing out pretreatment and source control of concerning elements and chemicals is important. And as we manage biosolids, we can focus on the fact that biological processes tend to increase the destruction of trace chemicals of concern. So anaerobic digestion, composting, and then application to soil can all create different biological conditions that break down different chemicals. As we manage biosolids, these are the kinds of best management practices and regulatory requirements that are out there to ensure that biosolids have as little impact as possible in terms of negative concerns of trace contaminants, and do the best in terms of providing nutrients and organic matter to soil. So the biosolids are applied at the agronomic rate. That's the amount that the crop will use, and that limits the amount of total CECs. And maintaining setbacks from surface and groundwater is required and is best practice. Applying to aerated soils helps with the microbial breakdown, and following research and updating the BMPs is important. So my last slide is basically showing this. So biosolids recycling is an option. It's been widely used and demonstrated to have many benefits. However, there are trace contaminants in it, and we need to manage those and continue as responsibly and effectively as we can. But the big picture is important. Would you prefer to have landscapes, for example, at the top here, which remain unusable or minimally usable and not very productive, or in this case where one-time biosolids application created a ongoing long-term ecosystem that's functional and effective and supports wildlife and human activities? This is a good choice, and CECs were there in these conditions and have been there in biosolids, and PFAS have been there in these kinds of projects in the past and continue to be, but are they disrupting the benefits? I think generally not, is what we're seeing from the research. So thank you for your time, and depending on how Beth feels about it, I'm willing to address a few questions.
Hey, Ned, thanks for your presentation. Lots of vast, wonderful information about biosolids. Yes, we can take another 10 or 15 minutes for questions. Before we do that, and while everyone's typing in, did you want to share that other info you were showing me earlier?
Yeah, I'll mention that the slide set includes some acknowledgments that I'm showing here and some various resources, especially on PFAS. So look to that if you're interested. There's also at the end of the presentation some summary data tables on PFAS levels in various matrices that you may want to look at. I'll also then just briefly mention, as you were reminding me, that the current coronavirus situation is obviously impacting everyone. There's particular essential functions such as wastewater treatment that are obviously impacted and are needing to pay attention. And I just, for anybody in that field, in that profession, or anyone else interested, the Water Environment Federation has an excellent website they are updating regularly on coronavirus and the impact to wastewater. Generally what's needed to be safe at wastewater treatment facilities. Generally, there's no evidence that virus survives the disinfection process or drinking water and wastewater, but continue to use normal protective gear at wastewater facilities and in managing biosolids, for example. And that should be protective. That's what NIOSH and others suggest, that the existing protective processes that we use at wastewater facilities should be effective against coronavirus. So pay attention to that. One of the other odd things that's come up related to coronavirus is that people are sometimes using their toilets as trash cans for the disinfectant wipes that everybody's using in great numbers these days. Toilets should only receive human waste and toilet paper, and that's it. The run on toilet paper that's happened in some situations has probably led to some people putting paper towel and other products down the toilets as well, which is understandable. So the run on toilet paper has had impacts. The reason these things are a problem, these paper rags and other materials besides human waste and toilet paper is that they clog pumps. They actually create somewhat dangerous situations for our wastewater workers. So please spread the message that toilets are not trash cans. Please only put human waste and toilet paper down them. Please throw any other, even if they say disposable on the package, please put them into the trash.
Thanks for that public service announcement. I'll dive right into the questions, and I will apologize ahead of time for any mispronunciations. So our first question is, at Joint Base Cape Cod, the source of PFAS and PFOA in the Ashmont Valley plume include former fire training area, wastewater treatment plant, and water sediments in Ashmont and John's Ponds. This has greatly increased the size of the plume and contaminated public-private drinking water wells in Falmouth and Mashpee. Would this occur in the use of biosolids in agriculture and forestry?
No. So again, that's a good example of the distinction between an industrially impacted PFAS site, where both firefighting and industrial activity with wastewater got into the Cape Cod aquifer and is contaminating wells, and that's a significant situation that has been and is needing addressing. The levels in the groundwater there, I think, are in the hundreds or thousands, as I recall, though don't quote me on that. A typical wastewater or biosolids land application site, really irrigation using treated wastewater, will not have levels like that, unless in the rare case that they have a large industrial input to those wastewaters or biosolids. So there's a real difference between these industrial and firefighting impacted sites and the levels in groundwaters and drinking waters around them versus a typical biosolid site.
Okay, next one online is regarding the PRZM leaching modeling. Do you have any field data to support the modeling results?
Yeah, part of that initial modeling did show what was calibrated some with one study out of Ontario, which was the one sort of field study we could find in the literature. Gottschall et al. 2017, I think it was, Ed Top's group, that gave a sense of the leaching in the real world biosolids land application scenario. But we haven't gone further with that, with publishing or making it definitive statements about that modeling effort, because of the fact that there is we have just that one calibration going on, which seems to verify that the model is pretty predictive, but further field data are needed to ensure that it's properly calibrated.
Next one, a comment and a question. Great talk, very informative. Would like to know more about the incineration options since land application is not available in some cases. What are the conditions for biosolid incineration, and does PFAS degrade during incineration or high temperature treatment?
So this is still being researched and debated. The understanding from the literature is, and from what I've heard from others as well, reviewing this, is that PFAS are generally need a temperature of about 900 to 1,000 or higher Celsius, 1,800, 1,900 or higher Fahrenheit, to be destroyed. That means to break the carbon-fluorine bond. Otherwise, lower temperature incineration is basically most likely putting the PFAS intact into the air, and then it may or may not be removed depending on the air emission control systems. So it may remain a concern in one of the matrices coming from an incinerator. Most wastewater sewage sludge incinerators operate at temperatures lower than that temperature required, but we're not sure, and it appears in those situations that the ash, limited testing has shown that the ash from the incineration process of incinerating sewage sludge ends up not having the PFAS in it, so it's likely caught in the air emission systems or goes into the atmosphere. Further testing is being done on that to understand. There are some incinerators that do operate at higher temperatures and may be destroying the PFAS, but again, more research is needed. And pyrolysis and gasification systems and others like that, same questions are still out there as to whether the PFAS is destroyed or just displaced to the air emissions.
Okay, next question is, will the use of cover crops and no-till on agriculture fields have any influence on the breakdown of CECs?
That's a good question. So cover cropping and no-till, I'm going to go out on a limb a little bit. It's not. I mean, I certainly have read quite a bit, but it's not. I'm not a agronomic research scientist. But the microbial activity that's generated when you have no-till and cover cropping, that tends to build a healthier ecosystem than a lot of commercial farming, traditional commercial fertilizer farming. So that enriched, healthier, more biologically active soil should improve the breakdown of CECs in the soil.
Are there any co-contaminant interactions for PFAS with contaminants in soil water systems?
And that's beyond my expertise. Again, having read a little bit about site cleanups and regarding PFAS, there is a lot of question and research being done on co-contaminant impacts and fate and transport, and it's, I think, pretty much understood that yes, those co-contaminants will impact the fate and transport of PFAS, which is not surprising.
Okay, comment then. Question, composting may help some CECs. How about producing biochar from biosolids?
So biochar is produced through pyrolysis or gasification, and it's a solid portion of that comes out of that process. That process of pyrolysis and gasification will break down a lot of CECs, different CECs than perhaps than composting would, for example. I think likely because that physical and chemical process of pyrolysis and gasification is pretty intense, that a lot of trace contaminants will be destroyed, and some more persistent ones may go into syngas or the gas phase of the pyrolysis process. But yeah, I think biochar has a particular use in some, and those processes have particular use. They are energy intensive, and so the balance of benefits and risks has to be evaluated.
So that was the last question that came in. So Ned, I'll thank you again for joining us for the webinar. And what final thoughts would you like to leave us with?
The last statement I would make is that biosolids recycling is something important to a lot of wastewater facilities and communities across North America. It's an important function for the circular economy, and we're doing what we can to address concerns of emerging contaminants and PFAS in particular. And we're hoping to see improvements happen that are protective of the environment and public health, but that do not result in total elimination of very effective programs that have been in existence for decades.
Thank you.
Thank you, Beth, and thank you all for listening.